Now we will consider the design constraint for the additive manufacturing of metals. So of course, there is some freedom regarding the design for additive manufacturing that we have discussed before, but however, we still have some kind of limitations which are listed below for the an example of powder bed fusion using laser as a heat source. For example, no free floating part in powder bed. Yes, this the and you see because the part is has a certain weight, and if you do not anchor or fix the position to the building substrate, and then you would have some kind of failure. Yes, some kind of failure. So at least you need to fix the position of the part, yeah, to the building platform, and the surrounding powder bed cannot be used as the support structures. And if it collapses, so you throw everything away. So you need to design the support structure, especially for the bed fusion. Yeah. Support structure need to be rigid enough to withstand the stress, but fragile enough to be removed after the 3D printing. Yeah, so need to find a trade-off. Yes, during the 3D printing process, this can also be used as a mean, transfer the heat to the building substrate to how can I say reduce the temperatures of the part and to reduce the thermal gradient in between different regions of the part, and therefore reduce the residual stress accumulated inside the part after the fabrication process. So support structure is quite important. However, support structure in many cases can be considered as the waste materials. So on one side, yeah, you design support structure in order to support the part. But on the other side, you have to minimize the amount of support structure to save cost and time for fabrication, because after the process of 3D printing, you need to remove the support structures. So let's say the larger amount of support structure, the longer time you need to post machine the part to remove uh, these support structures. Overhang is the term describing those surfaces which are down facings, and these surfaces need support structures. Yeah, but then yeah, generally speaking, the software can help you in order to generate the support for those down facing surfaces, but then this also requires some kind of experience, uh, and you can perform the simulation inside the software, like for example NetFab or Materialize, to see that if there is any deformation during or after the 3D printing process, and if maybe the case, and you need to enhance the support structures, amount of support structure, yeah, to make the more rigid structure that can be subject to 3D printing. Otherwise, otherwise you would have failure. Yeah, failure. So yeah, you have to play with it. You have to play with it. Pots and powder release channels must be provided. It means that you need the channel or the pipe inside the pot, and you have to get in order to release all of the powder inside the channel or internal volume, and take them out of the pot after the 3D printing process. So these the manufacturing features. These feature exist at the manufacturing process, but there's no function during the operational phase. No function during operational phase. The part orientation affect part qualities of coating layer. Yes, surface quality, staircase effect. Yeah. So here is a little bit hard to explain, but in the next few slides, we will talk about the staircase effects, and these will be regarded the part orientation and the selection of the layer thickness. The larger the layer thickness, and the higher the staircase effect you would have. Minimum wall thickness and feature size must be respect for each type of material. So let's say for example, the case of aluminum silicon 10 magnesium, and you use the particle fusion as is by laser. Um, the minimum wall thickness in general 1 millimeter, and if you create the feature having size, let's say 0.5 millimeters, and then you would have proper, because the 3D printing machines cannot be used in order to fabricate those thin structures or small structure which have the size smaller than the minimum wall thickness. No. Below this value, you would have risk of defect, higher risk of defect. Sometimes it may be okay. You have the product, but in many other cases, you will have failure. You will have failures. Side building chamber. So especially this is the issue of particle fusion, because the size of the building chamber will restrict the size of the part. So everything needs to be fit on or in the building chamber. So if you have the larger part, for example, the frame of the bicycle, yeah, the main frame of the bicycle, and you could see that you could anticipate the size or the length is around 1 meters in length, around half meters in height, for example. So how can you fit into the building chamber of, let's say, 280 millimeters, so around 30 millimeters, so 28 centimeters, I'm sorry, 28 centimeters. And one of the possible thinking is to divide the part into different sub-parts. So you should design into different smaller parts, and then you join them together after the 3D printing process. Yeah. And the other constraint is if the part has the rapid transition in the thickness, so you may have some kind of distortion. Rapid transition in thickness. The hole size reasonable apply for drilling, tapping during post machining. Yeah, to satisfy the dimensional requirements. So that's what you have to pay attention to, because they are the challenges or the limitation regarding the AM process and so on. So if you work with this, and you could see there are many more, but depending on the part having feature that you are designing, some you may have to face with one or two limitations. The other, yes. The other design constraint for the wire fit electron beam and arc direct energy deposition. Firstly is the accuracy of the process, because we have large mountain pole. So it's suitable for the part with large sections. So with the thin sections, so we have the heat buildup and it's easily to be distorted. Large mountain pole, you have the building from the flat surface. Uh, and here, overhang features may not be fabricated without process interruption. Just be careful, because we have large mountain pool And on the edge of the pot, yes, the molten material can pour or drop, and you have some kind of defect on the external surface of the pot. Should accounts for a large distortion and cracking due to the residual stress. Yeah, because you have large molten pool, you have the heat buildup, you have the residual stress, and if the stress is released and you have the distortion. Slow cooling of the large pot, and yes, slow cooling is mean that the temperature of the pot is high. It means that the pot having or the pot has the high free give energies, and the energy is provided to the atoms. The atom can diffuse from a certain grains to another and promote the grain growth process. So, and small grain, smaller grain, better strength, grain growth, strength reduction. Yeah, and then you have to consider long cooling time. Yeah, diffusion. Yes, because at high temperatures, the diffusion can occur. And if it is the diffusion of hydrogen to the bulk material, and please remember that hydride phase phases are in general bridge phase. So, and if these hydrides are accumulated in the boundary region between grains, so is detrimental factors to the properties of the material. Ribs and support structures may need to support a section which tend to rough. Yeah. For these, for example, down facing the surface, this may be required, the support structure. Yeah. But then it depends on the parts that are subject to the manufacturing process. But in general, there's some constraint that you may see uh, when you work with a wire feed electron beam or arc direct energy deposition. For the direct energy deposition using the laser as a heat source, so you should have the constraint. The design constraint is the clearance, the hair, the powders, and the laser head. Will affect the orientation of the view and path geometry. Reduction in the resolution, constrain the edge geometry. Yes, generally speaking, comparing to the case of product fusion, the direct energy depositions have lower resolution, and therefore the qualities of the edge of the part is lower as well. Yeah. The spot size is larger than the case of powder bed fusion. Yeah. Knowledge of center of gravity may require for parts, yeah, being articulated. Yeah, fixture and clamping may be needed for the basic stem. Yeah, maybe need. It's not always need. So it's just some points that you may face with, yeah, when working with the direct energy deposition. Yeah. Integration of base feature to final design. Yeah. Some geometric features may not be built, yeah, comparing to the case of particle fusion. Complicating CAM design process, high-level expert. Yeah. And please remember that for the direct energy deposition, you have the M code, you have the G code. Yeah, you have to provide some kind of coding. Yeah, to control the movement of the machine and the so on. So you need high level programming. So not in the case of Paradigm Fusion, where you use the software in order to set up the motor. Yes, you perform the slicing process. You transfer the file to the setup file to the AM system, and then activating the system and push the button to start. And yeah, that's all. Everything has two side effects. Yeah. So yeah, additional design requirement. So we have talked about the support structure design. Uh, yeah, generally speaking, this is said that this is a critical step for design because if you uh, do not design enough support structures, then part can be distorted or the down-facing surface will have a rough or poor qualities after the 3D printing process. So, so you need time to practice. You need time to gain the experience for creating support structure for certain design. You need to play with the process. And typical requirements for Butterfly Fusion. And this matter of heat transferring to the surrounding powders and and due to the, the heat dissipation to the adjacent powders, the adjacent powder can be consolidated. And if the powder surrounding is somehow stable, and you may not need support structures. So this is more or less in the case of direct energy deposition. And despite the fact that you use the computer-aided design process, but intrinsically the design process of support structures is a trial and error process. So you have to try, you have to test, and this is the error, and you have to test it again. Yeah, that's why you need experience of designer, and you need the skill, kỹ năng, yeah, to optimize the process of support generation. And building support may consider as the time consuming process, let's say, especially if it's phase. And we need careful consideration. Yes, so I would say this is not easy. Yeah, we have to test. That's the reason that we should scale down the stat to set the material to speed up the process of fabricating, to check whether the support structures are enough for fabricating a certain part or not, whether or not is support enough for the number of down-facing surface of the structures. Desired fixture, jigs, and tooling. Yeah. Uh, but for sure, if you want, for example, uh, this is the van block on the right side, is the S build van block, let's say, and it is the van, and these parts need to be post machined in order to guarantee the surface quality or to guarantee the dimensional tolerance of the part, so that when you examine the one with the other external devices, and there is no leakage occur. So therefore, you need to post machine like the sealing surfaces, threading surfaces, yeah, and to perform post machine on the CNC system, for example, you need to fix the part on the system, and then in this case, you need a fixture. Yeah. For drilling, for example, tapping for creating thread, electrodischarge machining, wiring, and so on, grip for robots, and so on, and so on. Just some information for you to consider as an additional requirements for designing. And the others, we could see from here. Yeah. Yes, the cost, easy of remover, residual stress control. If you have a lot of residual stress, so the part can be easily distorted. To prevent the part from the distortion, you need to release the stress by performing, like some in the case of annealing, yes, to reduce the residual stress, thermal management, time to build, and so on. Test specimen design, yeah, like in the case of testing in material engineering field, uh, no matter how you design the materials, you need to test them practically to confirm about the properties of the material. So you need to create the test specimen uh, and require steps within the development process. So you can there is standard specimen which is designed based on uh, the standard you use actually. For example, ASTM standard or the ISO standard, X standard regulate about the shape and size of the specimens. And if you want to have some kind of certified result of the test, and you need to follow the instruction of the test based on a certain standard. So you need to refer to standard. And if there is a possibility to limit the size and shape of the specimen, and then you can save time, save material. Yes. But you need to guarantee that the reduced size specimen must represent a certain part function that's subject to be tested. Prototype design. Yeah. So prototype the design used to evaluate and optimize the design and to optimize the fabrication process as well, or at least to help to develop the fabrication process by modifying the processing parameters in the more appropriate way. To support non-destructive or destructive testing procedure to make change the design based on what we learn. Yes. So this is basically the optimization process or the development process. So we gain some kind of lesson or skill for each iteration of tests. Yeah. And through each failure, we have learned something. Yeah. That's why yeah we pay course to learn a certain lesson. The first prototype can be plastic to determine the form fit, and later we can prototype in method to test the functionality. So this the initial purpose of additive manufacturing. So uh, previously, yes, when the additive manufacturing technology uh, is not was not so well developed, and they at that time even used additive manufacturing for the fast prototyping, and just to see how the parts during the design process looks like to show to your boss, so for example, just to see the form fit. And later on, we can subject the part to the functionality test in the design condition, yeah, to verify the design. But now for the moment, it's no longer used to just for fabricating the prototype, but can also to fabricate the part that can be subjected to be used in practice. Rapid prototyping by the additive manufacturing can refine the design, speed up the redesign process, and testing the part and better final part. Yes, because you speed up the process, and therefore you have the high chance in order to create the better final part. Hybrid design, you can combine the additive design features and subtractive design features. So that's what I have mentioned several times. That, for example, in case of high pressure valves, so if you use the additive manufacturing to create the complex flow channel inside the valve, so it's okay. Uh, but then, since the valve work at high pressure, and if the surface quality of the valve is poor, especially at the joining area between the valve and the other devices, and you have the leakage in that case, and if you want to prevent the part from leakage, and you need to enhance the surface qualities just by combining the additive manufacturing with post machining, and that's the reason that you need to add more material at these surfaces which require post machining, and you have enough material to cut, yeah, or to mill or to polish, yeah. Modular design, so it means that to design in different modules to split up the big part into different small subparts. So this is the case, for example, when designing the frame of the bicycle, which is larger than the size of the building chamber, and it's necessary to design the large part which is bigger than the building chamber. And after the division process, you have the small part, and after printing out, and you assemble them together or to join them together. Cost analysis is someone we need to talk, but I'm not familiar with analyzing the cost because I do not sell the part. I do not provide any kind of service to earn money from customer. Yeah. Not up to this stage for the moment. Yeah. In the future, nobody knows, but for the moment. But some points, those can be discussed here. So several factors contribute to the AM meter parts cost are listed on the figure on the right top side of the slide. So material type, material vendor. So the more expensive material can be used, the higher part cost after the 3D printing process. Sure. Material vendor, part and support volume. Yeah, larger part volume mean larger part, large amount of material used to fabricate, and more expensive. Uh, the part the part is more expensive for sure. The head view parameters. The head of the part is actually affect the time for 3D printing process. If you have the so let's say for example a pen uh, like this, if you lay it on the building substrate, so the head of the part will be small with respect to the building substrate, and the building time will be short. But if you align the part vertically, yes, and and when you use the part bed fusion in order to print out the pen, the problem is that yes, it needs to go through uh, the multiple steps depending on the number of layer after the slicing process. So the higher the head of the part and 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 the larger number of the layers that the software defines, and the longer time which is needed to fabricate the part in the vertical directions. And therefore, you need to consider this issue. And the longer, this means that the larger the energy is used for running the AM system, the cost of the workshop, yes, and others, yeah. And these will contribute to the final cost of the part, and so on. Okay, let me concentrate on uh, those which are described here. So this is written here that cost estimation or business consideration for AM. So we have to consider the own process of product development for sure. Each one will contribute to certain cost of the final part, or contribute to the total cost of the part. For the conventional part, the costs are associated with the tooling and process development, production, and sale for sure. For the AM part, we can reduce the cost associated with tooling because we have the one, so let's say one or two step for fabrication. So for the general part, we can fabricate directly with additive manufacturing. For the for the others, which require a higher surface quality, and we can combine with post machining. And in that case, we need to this is predict that the cost will be enhanced, but not so uh, as significant as in the case of traditional manufacturing process. Maybe consider like this. However, there is uncertainties associated with the total cost of AM part, material, designing, and printing. Yeah, uncertainty. Không chắc chắn. Yeah. Because it depends on the design of the support structures, and support structure can be considered as the waste material. So the thing is that you should design the part so that these down-facing surface can be self-supported. Yeah, can be self-supported. It's the best way of the design, but it is not always possible to do. So you should have to find another method in order to support the down-facing surfaces. Yeah, it's not easy. It's not easy. It needs time, cost probably because uh, mistake means waste of material. It means that you yeah, it's a matter of money. Yeah. Wide range of price with respect to the powder quality, quantity, and purities. And in general, the cost of feedstock material in the form of powder is 2 times the cost of the wire and almost 4 times the cost of the commercial safe materials, like in the case of commercial sheet, pipe, angers, steel, for example. Yes, because they are the commercial products. They are widely fabricated, so they are widely fabricated. So the price is cheaper comparing to the case of powders. Yeah, powder is quite detrimental to the human health. It's quite hard to store in appropriate way. Yes, and for the traditional manufacturing process, people do not use powder. So we rarely observe in on the market for powders. Yes, that's the reason that the cost of the powder is high. Yes, for sure. The cost of AM meter printer, $1 million. Yeah, not really $1 million for the moment, but for the SLM system with a building chamber of around 280 millimeters, this costs around 500,000. 500,000. euro. Yeah, 500,000 euro. Not really $1 million, except for the complex systems like the AM production lines, for example. And but if you add the cost for not only purchasing machines but also the setup and running, yes, it can reach $1 million. And the cost you may spend up to $10,000. But of course, it depends on how many kilograms powders you have purchased. It depends. Additional cost for machine recovery, machine operator, consumables, yeah, lie in the inert gas and maintenance cost and reparation, yeah, for sure. Yeah, there are many types, of course. Laying the part down, which means that, for example, if you have the pen like this, lay the part down. This means that the number of layer is reduced, so you can speed up the building time. You can speed up the process or reduce or shorten the building time. A light part, a lining part with respect to a blade may require to spread uniform powders. Yes, yes. And here on the right side, you see the relation between the total cost and the number of the parts. And for the conventional products, if you fabricate the small lots, and then the cost of the parts will be extremely high. So on the contrary, those parts which are made of AM is pretty cheaper than in the case of conventional parts cost, because using additive manufacturing process is suitable for fabricating small lots. So the price can be so the part can be customized without uh, specific specifically customized without significantly enhancing the cost of the parts. Yeah. Yeah, cost analysis. So you can read it on your own. Yes. And now I would like to turn into almost the second part of the chapter, showing the more specific consideration for the design for additive manufacturing process. So we consider based on the engineering approach. It means that we design the parts, based on the requirements during the operational phase. Yeah. What about the ability of withstanding external load? Whether the part need to work in a corrosive environment, whether it need to withstand high temperatures or not. Yes. So we have to design several design aspects. So we have to design the geometric shape, size, yeah, size or dimensions. So we have to design also the process parameters, yes, because the process parameters also uh, has have some kind of relation with geometric features. Like for example, the larger the layer, the thickness. So we have the poorer the surface finishing quality for the S-view part. So and as a result, we have to consider the design. Let's say design considerations, because these selections, uh, uh, let's say parameters or features, will have certain influences on the accuracy, surface roughness, anisotropic properties, build time, and cross sections. Yeah. And therefore, we need to pay more attention uh, to the design for AM process. And we have more than 180 parameters. Yes. Each one can be modified. So how many combinations do we have? Oh, many. So there's one option is to use the parameters which have been developed by the AM printer supplier. The other, like many researchers are doing at the moment, is to investigate and influence of a certain parameters on the final quality of the part. So actually, they are doing at the moment. If you want to save cost and time, just refer to the parameters suggested by the printer suppliers. You can save cost and time. But then the number of materials can be limited because when you change the processing parameters and you would have another type of parameters since you have different properties, of the material after the 3D printing process. Lấy ví dụ như là món cơm rang chẳng hạn, đúng không? Cơm rang với gia vị A thì gọi cơm rang A, cơm rang vị B gọi cơm rang B, mặc dù đều là cơm rang cả, nói vui thôi. Cho nên là khi mà các bạn modify cái process parameters thì chúng ta sẽ có các cái sản phẩm khác nhau ở đằng sau, và các cái sản phẩm khác nhau ở đằng sau đấy thì nó khác nhau ở cái độ chính xác, ở cái chất lượng của bề mặt gia công, đúng không? Hay nói khác là cái độ nhám bề mặt, ở cái tính chất dị hướng, tính chất theo các phương khác nhau thì khác nhau, đặc biệt là cái orientation và dẫn tới là cái building time khác nhau và cái cross section. Yes, layer by layer fabrication approach. So in the unseen, the AM is rely on this approach, and the geometry qualities depends on the resolution. Yeah. And these actually affected by the layer thickness. And if you can see, how can I say, in the bottom of this line, on the bottom of this line, on the right side, let's say, if you have the vertical features like this, so there's no problem. But if you have something like the overhang features, or you have the down facing surface, yeah, and on the left side you have some kind of a stair, and if you enhance the layer thickness and you enhance also the staircase effects, which made the surface of the part after the 3D printing more rupture, not more rupture. Smaller layer thickness mean higher geometrical accuracy. Yeah, for sure, because if you reduce the layer thickness T here, so you enhance the accuracies, you enhance also the feature resolution. But there's not always possible to reduce the layer thickness, because you for certain head, if you reduce the layer thickness, this means that you increase the number of the layer, so you prolong the processing time, you prolong the build time. This matter of course because you prolong the time, building time is longer. Smaller feature angle, it means theta angle, significant staircase effects, because you have here the distance between the vertical edge here and the vertical edge here is farther, and therefore yes, it's made the staircase effect more significant, and you have less bonding between the layer. And the roughness of the size effect can be calculated as the thickness multiplied by the cos theta divided by 4. And for the butterbath fusion, sintering effect attack the powder. Yeah, this is the sintering. Sintering is mean that the powders are just joined, join it together just by locally melt in the contact regions. Yeah, in the contact region. So you still have the uh, the spherical shape of the powders, let's say. And if this powder attack to the surface and is negatively affect the surface quality. Yeah. And other errors is shrinkage during the melt solidification process. Yeah. And the shrinkage here is depended on the powder bed density or morphology of the powders. So that's why it's recommended to use the regular shape of the powders. So like the spherical shaped powder are better than the irregular powders. Irregular powder. So if you reduce, so there are the two factors that you need to consider here is the layer thickness and the angle features. Yes, you reduce the angle features, it means that the distance between the vertical edge here is farther. Yeah. At the same time, if you enhance the layer thickness, yeah, so you see the significant enhancement of the staircase effects, which make the poorer, which contribute to the poorer quality of their external surface. Mm. Poorer quality of external. And if you want to repair this situation, you need to add more material and to cut, to eliminate the stairs, and that's all. In metal butterbath fusion melting process, so for example, selective laser melting, energy beam like the laser beam or the electron beam moves along a pattern at high rate. Yes. So you have contour external, you have the hatch where you have the scanning strategy of the beam, of the energy beam. Let's see the scanning speed is too high. So just in 2 seconds from the starting point is stay at the ending point, for example, because it's too fast. And this leads to the existence of thermal gradient. Yeah, thermal gradient. This is the thing that promote the stress accumulation. Yeah. So the scanning strategy affects the temperature field characteristic. So in this case, you have the zigzag scanning. So the temperature enhance with enhancing the scanning vector length and therefore affecting the geometrical accuracy of the part. Yeah, and larger thermal gradient, you accumulate larger residual stress and lead to the distortion. Yeah, for sure. Let's simply think that you have the scanning vector, just consider vectors. In 1 second, the focus point here, from here, for example, to here. So it's moving quite fast. So the root of the vector is already cooled down, but the arrow of the vector is hot. So the difference in the temperatures in between the two regions of the path create a thermal gradient, chênh lệch nhiệt độ. And this is the reason that creating the residual stress. And this is the main reason contribute to distortion. And that's why we need to select the suitable scanning strategy. Yeah, scanning strategy for the laser electron beam. But for the best fusion AM process, yeah, is this is it's okay to have the positive dimensional error. This means that if you fabricate the part which is bigger than the design, so it's okay because you can perform the cutting process afterwards. But if you have the part having the smaller dimensions than the designed by dimensions, then yeah, it's material by the welding process, and then you cut because this is the additive manufacturing process. But it's not easy. It's actually not easy. Yeah. Okay. So now I'll let you have 10 minutes break, and then we can continue at, let's say, 1 past 2. So we have 1 day left. Yeah. The next week is the last day for the course, and we have to teaching our teaching hours left. Yeah. So I try to complete on time, and just everything. If there is some minor thing left, and you could read them at home. But I think we have enough time.